For millions of years, geologic processes have constantly reshaped the Earth. Slowly, forces acting within our planet have raised mountains and moved continents. Where the Earth's crust has been twisted and bent, minerals were often deposited in breaks and cracks within the rocks. Far below the surface, where molten rocks and gases exist, conditions caused atoms and molecules to be concentrated, creating pockets rich in certain minerals. Early man discovered minerals where they were exposed on the surface by the forces of erosion. Many hundreds of years before the birth of Christ, men were making tools with copper and bronze. Through the centuries, they also used the rarest and most beautiful of minerals in works of art or as decorations for the ruling class. Jade carvings from China and diamonds from India and Africa found their way into the palaces of Europe and often brought with them histories of mystery and intrigue. The Hope diamond is such a stone, famous for its rare deep blue color and the air of mystery by which it is surrounded. The stone is thought to have been cut from a larger diamond known as the French blue that was found in India and brought to France to be part of Louis XIV's crown jewels. In 1792, during the French Revolution, the stone was stolen and never recovered. But almost 50 years later, a slightly smaller stone came on the market that looked remarkably like the missing French blue. The new stone was purchased by Henry Thomas Hope, and although this rare blue diamond has changed hands several times, it still carries his name. Modern technology has developed many uses for minerals, such as ores as sources for metals. Coloring agents in flares and fireworks, or as abrasives and cutting tools for industry. Yet while man found many uses for minerals, most of his early knowledge about them was a mixture of a little fact with a great deal of fantasy. Alchemists believed that gems had condensed and fallen to Earth from nearby stars, and that metals and minerals were thrown off by other planets. Some minerals were even believed to quench thirst, stop nosebleeds, or cure snake bites. Slowly, however, the early philosophers learned to separate fact from fancy. During the Middle Ages, the first system of classification was developed, based on color, hardness, crystal form, and other obvious physical properties. Men like Abraham Werner, who organized mineral properties into systematic tables, and René WOE, who devised the first theory of crystal structure, helped to advance the new science of mineralogy. Finally, in 1854, James Dwight Dana published the System of Mineralogy, which for the first time systematically classified minerals in an organized manner, using only their chemical relationships. The Dana system, now in its 7th edition, is still in use. Today we know that most minerals are concentrated far below the surface of the Earth, where molten rocks or gases cool very slowly. Using a model, we can see what happens as the rapidly moving atoms cool. As they lose energy, the atoms move about more slowly, and the space between atoms gets smaller. As they get closer, the attraction between atoms increases until they begin locking together as solid crystals. So crystals grow where the minerals are concentrated in a molten state. When conditions are right, small clusters of atoms may come together, forming a seed. In solutions where only a few seeds form, the crystals will be large and well formed. But if many seeds take shape, the crystals will grow into one another, forming an apparently shapeless crystalline mass. Many common rocks, such as this granite, are crystalline, and their thousands of minute crystals have grown together, preventing the development of well-formed larger crystals. If we could see inside a crystal, we would find that the attraction between atoms forces them into organized patterns. The smallest number of atoms that form a pattern is called a unit cell. These 8 atoms form a unit cell for this crystal, and when repeated again and again give the crystal its symmetrical form. The symmetry of a crystal can be shown in several ways. First, a plane of symmetry divides a crystal in half, where each half is a mirror image of the other. If a crystal can be rotated on an axis to any position that is identical to its shape when it started turning, then that axis is an axis of symmetry. The center of symmetry in a crystal is a point on any axis that is equal in distance from the centers of 2 opposite faces. Years of study have shown that all crystals can be grouped into 6 crystal systems. Each system can be recognized because it has a unique set of axes about which the atoms arrange themselves in an orderly fashion. As the crystal grows about these axes, the length of each axis and the angles between the axes control the shape of the resulting crystal. This gives the minerals in each crystal system unique characteristics that make them recognizable. To see this more clearly, let's look at examples of each of the 6 crystal systems. The isometric system has 3 axes of equal length. The angle between each axis and all the others is always 90 degrees. Fluorite is one of the best examples of this system. Galena also shows well-formed isometric crystals. When one axis is longer or shorter than the other 2, and the axes are at 90 degrees, the crystals are classed as tetragonal. Many tetragonal crystals can be seen in this specimen of wolframite. And in this cluster of cassiterite crystals. In the orthorhombic system, the axes are again at 90 degrees to one another, but each axis is a different length. A good example of this system is barite. While these stibnite crystals clearly show axes of different lengths. The hexagonal system features 4 axes. Three of the axes are equal in length and separated from each other by angles of 60 degrees. The fourth axis may be longer or shorter than the first three and is always at 90 degrees to each of the others. We can see this in the familiar quartz. The monoclinic system features axes of different lengths, two of which are at right angles to one another, while the third is tilted at some other angle. Gypsum is typical of this system. Here is a single crystal, and here a cluster of crystals. Finally, the triclinic system has three axes of different lengths, and each is tilted at some angle other than 90 degrees. Axonite is a good illustration of this group of minerals. Many minerals show a preference for growth in a particular way. These growth habits are responsible for the wide variety of crystal forms found in nature. Minerals, then, are the result of natural processes. They are chemical compounds whose atoms combine in crystalline form, sources of useful products, as well as objects of great beauty.